All right. Let's start. I guess we won't do quite the declared topic. We'll do a kind of review of some of the things that we've talked about the last 2 days, or as best as I can remember it without much preparation. So we had these. What were they? We had these SUN Lie groups, right? What was so special about them? So, okay, you can think of them as these n by n matrices, n by n, with, oh yeah, thank you. Okay. That one's good, thank you. With complex coefficients, okay, such that they're unitary. So U dagger is the identity, and they preserve volume. So their determinant is 1. Okay. And I forget if you remember this, but that's okay. So this was the Lie group, right? I can multiply these together. They have, well, clearly they have inverses and so on and so forth. Then the one calculation that we did is we computed what the Lie algebra for them was. The Lie algebra, so this is, I guess, is going to be the claim. The claim is going to be that the Lie algebra, which people often write with these kind of lowercase, strange, stylized s, is matrices A, also with complex coefficients, same as above, but their whole thing is that A is equal to minus of the Hermitian conjugate. So this is dagger, not transpose. And their trace is 0. Okay. So I guess let's maybe try and prove these statements. And okay, this is thinking of them as like matrix Lie groups. The same is true for thinking of these as just like, instead of matrices, thinking of them as operators on some vector space, finite dimensional vector space. You still have a determinant, you still have conjugate, you still have Hermitian, you can take the Hermitian adjoint, and everything is still fine. So let's okay. So let's look at proof of this claim. Okay. So we want to compute the Lie algebra. What is the Lie algebra?
Generally?
Yes.
Some vector space equipped with
Yes, but in terms of the Lie group, what is the Lie algebra of a Lie group? The Lie group is some manifold, and
yes.
So the Lie algebra is the.
How it moves in that small space around the origin.
Okay, that's related. It's the tangent space at the identity, right? So SUN is the tangent space. Tangent space at identity of SUN. Do you agree? And so what we have to do is we have to figure out, well, what are the tangent vectors at the identity? Okay. So how are we going to do this? Well, we have our Lie group, whatever it is, and so say here's the identity. And so what we're going to do is we're going to look at paths, okay, that go through the identity at time t equals 0, and then find their derivatives. Okay, and then we're going to see, that derivative at 0 is going to be precisely a tangent vector. Okay? We're going to see what properties do the derivatives have to satisfy. Okay, and then hopefully we will be able to get this. So let's first look at the first. Let's look at the first condition. Okay. So okay, the first condition you may remember is equivalent. So u dagger being 1, this was equivalent also to the fact that the inner product of uv with uw is equal to the inner product of v with w, right? For all v and w. Okay, these two are equivalent. Yep. And I think before we prove things using this, okay? And there I didn't think of them as matrices. There I thought of SU2 as like a honest. I thought of it as like SUV, where it's really on some. These are linear operators, not just matrices, but it's all the same. You know, it's kind of like just you can pick a basis and then think of it as a group of matrices. So that's fine. So okay, in previous videos we've done a proof using this way. The proof using this way is much easier, right? So we say, so consider some path, a path u of t, okay? And so then, okay, if I know that u dagger, well, u of t times u dagger of t is always going to be equal to 1, right, this constant, then if I take the derivative of this whole thing, I'm going to get what? I'm going to get 0. That's right. But now I can just, this is matrix composition, right? By linearity, I can just take this derivative, right? Sorry. Yes. Oh, hello. Um, I can just uh, take this derivative and okay, we're doing mostly review right now, so so I can take this derivative and I'm going to get what? It's like I have essentially Leibniz rule, right? Because it's linear in each entry, so I'm going to have this dot times this plus this times this dot. So, and I want to take this derivative. Remember, I want to figure out what the tangent vectors are at the identity. And here we have u of t such that u of 0 equals the identity. Yes, the identity matrix. So that's E. So I want to take this derivative at time equals 0. Okay. So, okay, this derivative is going to be what? The derivative at time 0 times u dagger at 0, but this is going to be the identity, plus u at 0 times u dagger like dot. Okay, but it's the same. And this has to be equal to 0. Okay, but this is the identity, this is the identity. And so I get that the derivative has to be equal to minus the dagger of the derivative. Yeah?
Why do we not put like a 0 at the u dagger dot?
Yeah, I just don't want to. Yes, it is at time 0, but you know, this is precisely an element of the Lie algebra because it's the derivative at 0. Okay, so we've recovered this condition. What do you mean?
Like it's equal to negative, not just at the 0, but everywhere near it as well, right?
No, I don't think that's. Is that true? I'm not sure that's necessarily true. Wait, I think that should be true. Right? Because if I do a. No, that's not true. That's not true. Why? Because remember, if I exponentiate things, right? Like if I go further, I'll have exponential of at, right? And suppose I take a derivative of this, okay? Then this is going to be a e to the at, right? And so this thing has this property, right? But then this thing does not have this property necessarily for like t not equal to 0. At t equals 0, this is just the identity, and this has this property and everything's fine. At t not equal to 0, then if you take the dagger of this, you're not going to get minus of itself. And I mean, you can just look at an example where a is, I guess, I minus I. And then you can check, and it's not going to be the case, I don't think. Or actually, no. Maybe it would be. Maybe in this case it would be. But I'd need to check. Maybe that's not. Yeah, it's not necessarily true. Yeah, I mean, you can just like take the dagger of. Actually, no. I'd need since this has this property, for this whole thing to have this property, I'd need this to be symmetric. And it wouldn't, I don't think this would necessarily be symmetric under taking a dagger. So I don't think it's necessarily true. You'd need to check. Okay, good. That was this one. And then last time we kind of skipped over getting this condition, right? Now let's actually do it, since why not? You know what? Maybe this won't be a review. Maybe we'll still end up doing the initial thing I was hoping to do. So, okay. The second one, this trace being 0. I mean, we've kind of already used this condition. We've used this condition to get that. So surely I can use this condition to get that. Okay. Once again, we're going to take we know that always the determinant has to be 1. So we're going to take a derivative of the determinant of u of t at time equals 0. And, we expect to get 0. Right? So I'll just write that in here. Now, this can be a bit of a tricky calculation depending on what notation you use. So we're going to use kind of index notation to make life a lot easier. So we're going to sum over so all permutations and what are we going to do? We're going to have this epsilon sigma 1 epsilon n. So these are just so sigma 1 sigma n. This is just some permutation of numbers. So this is just some sort of numbers. Epsilon is this thing that is anti-symmetric, right? Like if this was 1, 2, 3, 4, 5, 6, 7 up to n, it's 1, and then if I swap any 2, then it picks up a minus sign, right? And I am going to multiply this by the matrix entries, u1 comma sigma 1 dot 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 u n comma sigma n. So essentially, I pick a number from each row, okay, and then multiply them together, and then multiply it by whatever correct sign of +1 or -1, and then add up over all such possible, choices of. I choose a number. Sorry, I choose a combination of numbers such that each number is in a different row and column. Okay, and so this is equivalent to the usual definition of determinant. You can check that it's like some alternating whatever. It's fine.
We have to take the derivative.
Yes, and now we want to take the derivative of this. Okay, but this is pretty easy, right? Because this is just like a bunch of things multiplied together, right? And I'm like a bunch of one single variable functions multiplied together. I can just use Leibniz rule. Do you agree? So if I bring the derivative inside, yeah.
Someone's asking if there's a Zoom meeting.
Oh, is there? I didn't set one up. I don't have one. Yes, I see. I can do a Zoom quickly. Okay, this will figure itself out in the background, I hope. I don't know, but let's see. Sorry. Good. Done. Share. Okay. Let's share this window. Okay, hopefully this is good enough. Okay. Right. And now what I have to do is, if I take the derivative inside, for a single permutation, for some given permutation, I have a second sum over j. Right? By Leibniz rule, what do I have to do? I take a derivative of one of the things, and then everything else is the same, and then I just take derivatives of different things. So I get something like this. I get, so I still have the same. Okay, let me make my epsilons more curly so they're more recognizable, distinguishable from all of these things. Okay, and then I have, okay, u1 sigma 1 as a function of t, dot, dot, dot. And then I have the jth one. The jth one has a dot above it. And then, okay, and I want to take all of these derivatives at 0, right? At 0. un sigma n 0. Okay. However, at 0, I'm the identity matrix. Do you agree? So at 0, all of these guys are 0 unless sigma 1 matches up with 1 and sigma 2 matches up with 2 and so on and so forth. Do you agree? So the only permutation that survives really is the one that has all the numbers matched up except for maybe in this jth entry. Do you agree? But suppose I fix some permutation, right? If even for suppose, yeah, I fix the permutation. Suppose for at least one of the coordinates it doesn't match up, right? Then all the terms are 0, except for the one where kind of the derivative is in the one spot that doesn't match up. But then if this doesn't match up with this, so like sigma 1 is 1, sigma 2 is 2, whatever, and only j is not the thing it has to be, right? And then suppose j doesn't match up here, so sigma j is not j, well then this whole thing would be 0 because then I'd have j somewhere twice. Is that right? No, not j. I'd have something else somewhere twice. So the point is the only terms that survive here are for the permutation, which is just where we do no permutation. Yes.
A question. The subscript, is that like the minor of that?
What do you mean the
like,
subscript?
You delete that row and that column, and then
So this is the entry in the first row and the sigma first column.
Okay.
These are just matrix entries.
Okay.
There's none of that, like whatever. I forget what it is. Okay, and so because at 0 this is the identity matrix, I only get the trivial permutation surviving, and so I just have a sum over. So for the permutation where we do no permutation, this is just 1. Yeah, and so I'm just summing over j of what? Well, all of these guys become 1, right? And so I'm really just summing over u dot j sigma j, not sigma, well, sigma j is j. right? Like this. But then that's just the trace of u dot. And so, okay, we know that that has to be 0 because this has to be constant. Okay? But, okay, this is useful. We've computed this derivative in general is the trace of the derivative of the matrix. Useful formula. Okay. And so we've characterized what the Lie algebra is of SU2. Okay. Yeah.
Question: is this like really the only way it's done?
What do you mean?
How do you not know there are more conditions on SU1 than just these two?
Well, okay, you can show, like, we've essentially showed that this condition is equivalent to this one, and this condition is, equivalent to this one. Like, if I have this, I'll have, yeah. Well, sorry, right. In principle, I should go backwards and show that if I have this, I'll have this, and if I have this, I'll have this. But that is actually, yeah, these two are equivalent. Yeah, because we just took the derivative, showed the derivative is 0. If you start with the fact that the derivative is 0, of course, this is going to be constant and equal to 1, and vice versa. So there shouldn't be any more conditions. Yeah, like we just showed that if you have this derivative. Okay, good. Right. So I don't know. Should I? Okay. Then the next thing we talked about was, I forgot that we have a waiting room. My bad. Okay, we're just doing review for the most part. Oh, and my mic is turned off here. Okay, now it's turned on. Good. We're doing review for the most part. Okay, so now, let me move this a little bit. Now we're going to look at the special case.
Wireless?
Yeah.
Yeah, I have wireless. Okay. We're going to look at
Now specialized to the example of SU2. So this is 2 by 2 matrices. Okay. It turns out, okay, and so we know that the Lie algebra, right, has to be these 2 by 2 matrices, which are which have this property that if you take the Hermitian conjugate, you get minus 1, minus of itself. So in fact, this means, specifically in the case of SU2, that this is just the span of the Pauli matrices. Well, the Pauli matrices multiplied by I. Sigma I. Okay. Where the Pauli matrices are what? The Pauli matrices are 0, 0, 1, 1, right? Sigma 2 is 0, 0, I minus I. I always forget where the minus is. And then sigma 3 is 1, 0, minus 1 is 0. Okay, these are the three Pauli matrices. And we can write the Lie algebra as some linear combination of this with real coefficients. Linear combination of this with real coefficients. Okay. So in the book that I've suggested, they introduce this notation that xi is, I think, minus I over 2 sigma I. Okay, maybe I should use j. And then Sj is equal to minus, or just I xj. There we go. Okay, so Sj is essentially just Pauli matrices divided by 2. So what's the advantage to using Pauli matrices versus these xj's? Well, Pauli, so these guys have the property that I take the Hermitian conjugate, I get minus itself. This, you can check, will have the property that I take the Hermitian conjugate, I get itself back. So these are self-adjoint. These are Hermitian, these are anti-Hermitian. Okay. Hermitian matrices are nice because they have a what for them? A self-adjoint matrices have the nice property of having a blank fact for them. Yeah, but they have a nice fact that you spent some time in 247 proving.
This thing. Orthonormal set of
That's right.
Oh yeah, orthonormal set of
Eigenvectors. That's right. So you have a spectral theorem for these.
Yes, that thing.
That you can decompose it into is diagonalizable. Okay. This, I mean, if this is diagonalizable, then of course xj has to be diagonalizable. The difference is this has a spectral theorem where the eigenvalues are real. This will have a spectral theorem where the eigenvalues are only have an imaginary part. Right? That's it. Yes. And so this would be, okay, this is slightly nicer to work with for some physical reasons, but actually we'll see that this will be nice to work with when classifying representations of SU2, which we'll see in a second.
Sj is just x, dx multiplied by j, multiplied by I.
Yes, actually, yes. It's just a matrix multiplied by I. That's it. Yes.
Wow, all right.
Yeah. Okay. So let's maybe write down some statements for them. The main statement is that, okay, if I take x1 commutator with x2, I'll get x3, and like any cyclic permutation. So essentially, xi with xj is epsilon ij k xk. Okay, so once again, epsilon ijk is some number which is either 1 or -1, depending on the sign of the permutation of ijk. 1, 2, 3 is 1, and then if you swap any two from there, you get a minus sign. Okay, and then these guys have the property that IS1, IS2 is equal to IS3. So, okay, the same thing, but I. Okay, don't confuse this I and this I, they're different I's. Good. Right. So now, okay, this was a kind of helpful review maybe. Yeah. Now let's actually, how much time do we have? Okay, we have some time. Now let's actually talk about classifying the representations of SU2. And we'll need all of this. So I'll kind of keep it here. Good. So how are we going to, first of all, let's recall kind of very briefly on the side here, what was a representation of SU2, right? So, or of any group. Representation of a Lie group G, right? What was it?
From pi to pi, the function from the group to invertible
Yeah.
matrices and
Yeah, so let's say over some vector space. So representation of G on some vector space V, okay, was some, specifically for a Lie group G, this was a smooth map. It was a smooth homomorphism. I'm going to use rho because I'm going to use rho, and yeah, so G times H is equal to rho of G times rho of H, and then you have that this works nicely with the inverses. So the inverse of the mapping, the inverse of the element, is the inverse of this matrix. Okay, rho of G is some, well, either some matrix or some linear operator, invertible linear operator. Okay.
Is that a condition of homomorphism, or is it something we just
plug in the identity?
Hmm?
Wait.
This is just what a homomorphism is.
Okay. Thank you.
Okay, but then I want this all to be smooth. Okay, good. Now, then we realize that for a Lie group, this kind of representation induces a representation on the Lie algebra, right? How did we get this? Do people remember? So this
Representation of the algebra was from the Lie algebra to all the endomorphisms.
yes, and what was that? What were endomorphisms?
Endomorphisms. The entire. Oh no, was it?
Yeah.
Wait. That's so.
Of Lie algebra. So I'm going to denote this with like a little star at the bottom, which means something, but whatever. So it's from the Lie algebra into the endomorphisms. The endomorphisms are just all linear operators. And in fact, this is just the Lie algebra of GLV. Do you agree? So this representation, all this is just I take the derivative of this map at the identity. That's all that map is. Right? Like I had my Lie algebra, my Lie group. Okay, and then I map into, matrices. Okay, and then somewhere here I have the identity matrix. Okay, somewhere here I have the identity. Okay, and then this is going to get mapped to this, and then I can look at how, this the Lie algebra here gets mapped to the Lie algebra here. Okay, and so this is precisely rho star. It's some linear map. Okay, so rho star, this is some linear map, and one of the big properties that it has, which actually follows kind of from definition. We define the Lie bracket this way essentially, but that this preserves the Lie bracket. Okay, meaning that what? Meaning that, so key property, that if I have the Lie bracket of two elements A and B, and then I do rho star of this whole thing, this should be, and so this is the Lie bracket in G. This should be
bracket of rho star A.
Yeah.
Rho star G
In the in whatever the target space is. Yeah, in little GLV. Okay. So okay, that's fine. Do you agree? Okay.
Why is it all linear operators?
Because if you have an invertible linear operator, right, and then if you take a at the identity and suppose you're at the identity, what directions can you step away from in the at the identity to still keep it invertible? In fact, you can change around any entry in the matrix, and it's still going to be invertible. You can change around any entry in the matrix a little bit, and it's still going to be invertible because the determinant is continuous, right?
Yeah.
So I can change my matrix around a little bit in any direction. So I can add any linear operator to it if it's sufficiently small, and it's still going to be invertible. So I can step in any direction.
Like a topological argument that like you're in the same like open neighborhoods, and that's why you stepping a little bit in the if you shift it a little bit, if you tweak a little bit, your determinant changes a tiny little bit.
Yes.
Continuous topologically means you're still in the same like little open set.
Yes.
So you are still in the same open set here, which happens to be actually the closure.
Yes. So that's it.
That's so cringe.
I mean, it's like just continuity. There's nothing to it. Okay. Okay. Good. So now that we have this, my question is, what I want to do is I want to look at all the representations. I'm going to actually I'll write this down somewhere. Where should I write this down? Yeah, I'll write down the question here. So the question is, I want to classify all unitary representations of SU2. In fact, you don't technically need to. The classification is the same, even if I didn't assume the representations are unitary. But then there's a bunch of like some small details which I think would distract a little bit from the main point.
It's the same
So,
something.
yes, it's like the classification, all the possible representations you get, like how they look like, are the same. You just have to show that if you have some representation that's not unitary, it's equivalent to one that is unitary, and that is just a small detail that I don't want to think about. Well, I thought about it last night and decided I don't want to have you think about it for now. What does it mean to be a unitary representation? Remember, for a unitary matrix, we have a notion of taking a Hermitian adjoint, and right, and so representations of SU2, so on vector spaces over the complex numbers. Okay, so we're going to have a vector space over the complex number. It's going to be an inner product space. So it's going to have an inner product, okay, over the complex numbers. And so this has, now the vector space, the matrices have some notion of taking an adjoint. The linear operators have some notion of taking an adjoint. And so what I'm going to mean is that if I do row of U dagger, then that should be row of U all dagger. This is what is meant by unitary. Okay, that it plays nicely with this dagger thing. Okay, and in particular, it means that if a matrix was self-adjoint, after I push it with the representation, it's still going to be a self-adjoint matrix. Okay, and all these things like self-adjoint matrices get mapped to self-adjoint matrices, anti-Hermitian matrices get mapped to anti-Hermitian matrices, and so on and so forth. So this just simplifies life a little bit. Okay, so I want to kind of like, by classify, I mean I want to tell you how does each representation look like, roughly. Like if you give me a representation, is there a nice way to break it up into pieces which I understand really well? Okay. And we're going to do this, with the help of all of this stuff. Okay. So first thing is, actually, instead of, so we had, this is better, I think this is better. Okay. Before, so we want to classify representations of SU2. The thing that we never really discussed, but the point is, it's a fact that SU2 is simply connected. And because it's simply connected, don't worry about too much why at the moment. Turns out this is like the Lie algebra contains all the information about the Lie group. Lie group. Okay, because it's simply connected. Just being connected isn't enough. You need to be simply connected. But the point is, instead of classifying the representations of the Lie group, I'm just going to classify the representations of the Lie algebra. Okay, so I will sufficient to classify row star instead of row. And row star should be, in principle, much easier to classify because, like, Rho, this is like some smooth map that has some complicated property, whatever it is. But then rho star is much simpler. It's it's some linear map, and I'm just trying to classify particular kinds of linear maps. So that's somehow not as bad.
Rho star doesn't need to be a smooth homomorphism.
Well, yeah, yes, it has to be a smooth linear map. Oh, sorry. Well, sorry, it has to be a linear map, but linear maps are already smooth, right? And it's just a derivative. It's a linear map, so much simpler to work with. Okay, right? So, so let's see. So the Lie algebra, right? This is some vector space, some real vector space with. Oh, I'm muted. Okay, awesome. Okay, the Lie algebra is some vector space with dimension 3, right? Yes. And so then I times this are the basis vectors. Do you agree? So okay, we're going to somehow try and use the fact that this is a thing. And what else? Okay, so what do we need to really classify? We need to classify how does the Lie algebra, after being mapped to somewhere, act on the vector space that those matrices act on. Okay. For this thing, we're going to first do a few steps that I'm not going to explain exactly why we need them. I'm going to motivate them too well, but we can use them, and then soon it will become, after a bit, it's going to become obvious as to what we're doing. So step one is going to be to complexify this SU2, the Lie algebra. Okay, and by extent rho star. So complexify means, before it was a span with real coefficients. Now I'm going to allow complex coefficients. Okay, that's fine. I just add an extra I and then okay. But then this naturally, means I can complexify this linear map, right? I just assume that it's now linear with the complex numbers. Okay, I can factor out the I out of the rho star, and that is fine because our vector space is over complex numbers. So like the structure to do this is already there. Okay, and now in this so this complexification, this is actually a Lie algebra of another group. It's called SL2C, and this is the Lie algebra of what's called the special orthochronous group, something like this. It's related to Lorentz transformations, but I don't want to talk about this right now. Regardless, okay, we complexify this, meaning I just allow to multiply things by complex numbers here now. Okay, and now we're going to, the question is, how to, is essentially, instead of looking at how does, so instead of asking how does rho star of xi act, I'm going to ask how does rho star of si act, okay, on the vector space. Okay, I'm going to try and classify how do these guys act on the vector space. Now remember, Si was what kind of matrix? Self-adjoint. And because because this is a unitary representation, then this guy will also be a self-adjoint matrix. Okay. This whole matrix is self-adjoint. So it has a spectral theorem. Do you agree? So this is how we're going to start. Okay. So step 1. Okay, let's pick S3 and let's look at rho star of S3. Okay. This has a spectral theorem, so I can diagonalize. So I can diagonalize everything with this. Diagonalize, just diagonalize this matrix. So I get some basis of eigenvectors. Yeah, that's good. So now we're going to introduce the following definition. So suppose V is an eigenvector of this thing, of this matrix, with some eigenvalue.
Complex.
Hmm?
Complex.
The eigenvalue will be real
Oh.
because S3 is self-adjoint.
Ah, okay.
So the x's would have complex eigenvalues, but I'm rewriting this in terms of the s's. So they have real eigenvalues. I could write everything actually in terms of the x's. The story would be the same. Okay, so suppose V is an eigenvector of rho star S3 with some eigenvalue k over 2 of V. Okay. So, I mean, this is nothing fancy. And now we're going to, the definition is we call k a weight of this representation of we'll see why this is a useful thing to begin with in a second. Okay, but this is a matrix, it's self-adjoint, so there's some basis in which it's diagonal. Now, note that S3 does not commute with S1 and S2, right? So the commutator is not 0. So ideally, I could like diagonalize everything together, and then I'd be done. But I can't, right? So I can only diagonalize this guy at a time. So now let's see what else can we do. Okay, first let's make a few comments. First, V is so I forgot to say, but V is finite dimensional. I'll assume V is finite dimensional. This means V is finite dimensional. This implies there exists a maximum weight. Okay, there exists a maximum weight n. Let's call it n. Okay? And so what we're going to do is we're going to kind of like, there's like eigenvectors with different eigenvalues of this guy. And we're going to try and look at a particular subspace, right? Such that all three of these matrices preserve that particular subspace of this whole thing. Now, these three matrices are not going to preserve, a subspace with a particular eigenvalue, right? Because they don't all commute, right? But maybe I can pick a bunch of vectors with different eigenvalues, look at their span, and maybe that will be preserved by all three of these matrices, right? And so then I can kind of like, I have my representation on my vector space, right? These matrices act on this vector space, and I can look at a chunk of this vector space, which is which is invariant under all of these matrices. And so the goal is to take the vector space and kind of split it up into these chunks. Yes, we have done this before. It's all the same. Okay. And now how are we going to do this? And actually, this is the step that we've done before also many, many times. Is now we're going to introduce S plus and S minus operators. So S plus minus is going to be S1 plus minus I S2. So this is two operators. S plus is this plus, and S minus is this minus. Okay. This looks kind of familiar. We've seen this before. And now, the big punchline, well, one of the punchlines about S plus and S minus is the following. That, so once again, these are like these matrices but scaled, so you can sit down and, you know, check what anything is, check all of these commutators. But the point is that S3 with S plus, the commutator of that is S plus, and S plus with S minus is 2S3. Okay? And S3 with S minus, I think should be what, S minus or minus S minus? Sorry, let's just check this. So S minus is S3 with S1 is going to give me, sorry, where is S3? S3 S3 with S1 is going to give me minus S2. Sorry, is that right? I need I's. Yes, so this is, sorry, this is I minus, so S1 with S3 is going to give me IS2. Yes, it's going to give me something like IS2, and then I think minus S1 probably. So yeah, it's going to give me minus S minus. I'm pretty sure. Okay, if it's wrong, we'll check that. We'll see it. Okay, good. I need more board space, and I want to not erase anything. But okay, maybe we'll for the first time use one of those boards. We'll see. No. I'm not moving there yet. Don't worry. Okay, so we've done this, and what's the strategy going to be? So I have these vectors. I have this. Okay, I have these vectors, and I have these eigenvectors of essentially S3 of rho star S3. And what I'm going to do, okay, and then there's one that has this highest weight. Do you agree? The point is, okay, there's going to be vectors with these different weights, and you're going to see why it's. I'm jumping by 2 in a second. The point is, I'm going to want to take a vector here, and I'm going to try and use these S plus S minus operators to kind of go from this eigenvalue to lower eigenvalues, okay? And then I can use the other operator to go back up, and then this way I'll hopefully build like a tower of states, right? And I can use S plus and S minus to kind of go between them, and SZ kind of keeps me in one spot because they're eigenstates. And this means that I can kind of constructively like pick a vector, then generate a bunch of other vectors until I get some like kind of complete list of vectors, such that S plus, S minus, and a Z preserve the span of this list of vectors. Okay, and so I'm going to get that the representation is invariant on this kind of chunk of my subspace. Okay, and then I can just kind of do this to split up my my vector space into these chunks in which S acts in the S's act in a particular way. And so what I'll be able to tell you then is like how all of these chunks could look like, and yeah, that will be the goal. We will have classified the representation because I'll just tell you, if I have some representation of SU2, it can act on the vector space, and it can act maybe on chunks of the vector space in like roughly this way. Okay, you look like you have a question.
Oh no, I was just thinking like this entire approach of building all the other, or essentially finding the other eigenvectors.
Mm-hmm.
These are also the eigenvectors we use for spectral theorem. Oh, we can always apply spectral theorem. Okay. Doing this, like this only kind of started because we have sigma 1, sigma 2, sigma 3, right?
Yes, like the important part we're using is these commutation relations of sigma 1, sigma 2, and
Okay.
sigma 3.
Is this sort of always viable? Like, can we, if we are given something, I don't know, like
If you're given an arbitrary Lie algebra with some arbitrary commutation relations, I don't know.
I'm like
You may not be able to use this strategy necessarily. Right. This strategy is actually, this is essentially like kind of like creation annihilation
yes,
operators.
we started with
Yes.
something and then we built more by creating
Yes,
from
but
the
here we're
source.
kind of starting from the top, building down. Okay, so let's see what are the statements. What are the statements here? I'll draw a pretty diagram maybe later. More or less, yeah, that's fine. So today I'll just do like a schematic thing, and then we'll finish properly next week when we have maybe more people. So a few kind of lemmas. Okay, which you can check from the commutation relations. That okay, if V has weight K, okay, then S minus applied to V has weight is either 0 equals 0 or has weight K minus 2. And then similarly, S plus V has weight K plus 2 or is 0. Okay. Do you agree? So this is the statement. Okay. And roughly what's happening is, right, it's once again this picture. I have some maximal weight n, right? So this is kind of like some vector that has eigenvalue n over 2 with respect to this operator. Okay? And so I can use S minus to lower the weight of this vector. So if I apply S minus to a vector here, I'm going to end up with a vector that has eigenvalue 1 less. Okay? So S minus goes this way. And then I can use S plus, okay, to go back up, right? And then S3 kind of doesn't, keeps everything the same. Okay? And sorry, really I should be writing instead of S plus V, I should be writing rho star of S plus and rho star of S minus. Okay? I'm just being a little lazy. It's a lot of writing. Okay? And so the point is, we're going to have n minus 4, dot, dot, dot. We're going to have 0. We're going to have minus 2. And all the way up to like minus n. Okay? We're going to go all the way up to minus n. And actually, you will not be able to, so if n is the highest weight, then minus n is going to be the lowest weight. And this is something we're going to need to prove. And the main difficulty that we need to prove is that, what's the procedure? Procedure is I pick V with highest weight, and so with highest weight n. Okay. So I pick a vector here, and then the claim is the real claim of what I'm trying to tell you is that the span of V S minus rho star of S minus V and then rho star S minus applied, I don't know, whatever 2n times applied to V, that this is preserved by S minus, S plus, and S3. Well, rho star of all of these. What precisely could be the problem? The problem could be, suppose I start here with some vector, it's an eigenvector of S3. I can go down with S minus, okay? And then I can go back with S plus. And I know for a fact from like that theorem that I'm gonna have the right eigenvalue, but maybe there's like many vectors that have this eigenvalue, and maybe I go down, I go back up, and I'm in a different, like, end up at a different vector. Okay? Can you imagine like that could happen? The point is that doesn't happen.
Okay.
And that's the non-trivial statement that we would need to prove. Okay? And the problem is this doesn't happen. That's the first thing we need to prove. And the second thing we need to prove is that, okay, this has some minus n. Yeah, there's a lower, well, the fact that there's a lower limit is obvious, once again, because the vector space is finite dimensional. What is maybe not immediately obvious is that the lower limit is minus n. Yeah, and not something else. Okay. How do we prove absolutely all of these things? All of these things you can prove by induction. And what you do is you start at the highest, you pick some vector with the highest weight, okay? And then you bring it down by S minus, bring it up by S plus, show that it's the same vector. Okay, you do it all just using these commutation relations. And to prove this thing, which you can show, this last statement, I'll just write the statement. I won't prove any of them now because it's, I just want the conceptual idea to be clear, and then we'll prove things next week. Okay, is J n minus J plus 1 Vn minus 2 J minus 1. Okay, where Vn minus 2J is I apply S minus n J times to the some highest weight vector. Okay. So, okay, all of these things we're going to prove next time by induction. But the point is, if I have a representation of my Lie group, I have a representation of the Lie algebra. If I have a representation of this Lie algebra over some vector space over C, I can take, this vector space, okay, and I can kind of pick out some chunk in this vector space, which is made up of a bunch of one-dimensional subspaces. It has a bunch of one-dimensional subspaces. Do you agree? Which are indexed by some integer, which is the eigenvalue of this guy. And then these two guys, S plus and S minus, just let me hop between the one-dimensional subspaces. Okay, and so the claim is that any vector space I can divide up into some structure that looks like this, into a bunch of structure like subspaces which look like this, which are invariant under the action of the Lie algebra. And because they're invariant under the action of the Lie algebra, they also have to be invariant under the action of the Lie group. Do you agree? Right? Because I can, because SU2 is simply connected, I can exponentiate the Lie algebra to get the entire Lie group. And so the entire Lie group will then also only act kind of within the subspace, and it won't move anything from this subspace outside. Okay?
All right. You might have mentioned this, maybe I just went over my head. You only drew like a specific section of that vector space.
Yes.
And in particular one, can there be many?
Well, so the point is, if I take a vector, I get this chunk. Then I take another vector, I get another chunk. And so I essentially split it up into a bunch of chunks that look like this. So for example, suppose, so this is an example and then we're done. Suppose I had some three-dimensional vector space, and I had a representation of SU2 on this three-dimensional vector space. Okay, so I had SU2, which was acting on this three-dimensional vector space. Do you agree? Okay. So it's 3 dimensions, so I have kind of 3 things. What are the possible things that could happen? Okay, I could either have like 3 single, like the trivial representation, where SU3 just acts trivially on this guy and doesn't move him anywhere, acts on this thing, doesn't move it anywhere, acts on this thing, doesn't move it anywhere. Okay. The other option is I could have these 2 guys. This gets moved. Yeah, I should have a spin 1/2 representation. Yes, this gets moved here, and this gets moved here. Do you agree?
The last one gets moved itself.
And then the last guy, all of them act trivially on it and act as the identity or some scaling. And then the other option, I think, sorry, is this right? Is this possible? This should be possible. Yes. Yes, this is possible. Yes. Okay. And then the other option is that, this gets moved down, this gets moved down, okay, and then this gets moved up, and then this gets moved up, so like this. So there's a 2-dimensional chunk of the vector space that's invariant, and a 1-dimensional chunk of the vector space that's invariant, or all 3, the whole vector space is moved around by the representation. It's all parts of it are connected with this representation. So okay, I've now told you roughly how any representation of SU2 on a 3-dimensional complex vector space looks like. Okay, either it splits it up into 3 subspaces and acts trivial in each subspace, or it splits it up into a 2-dimensional subspace and a 1-dimensional subspace, or it kind of acts non-trivially on the whole subspace, and I can't separate it into parts where it doesn't. It's not invariant on any of the parts. Yes.
Just an extension. You can't cover the entire space with these chunks.
The whole point is that the vector space is the direct sum of all the chunks.
Okay, thank you.
So the whole point is that the vector space is a direct sum of these VIs, right? And then the representation can be restricted on the VIs. Yes.
It's just a small pushback. It's on the stair. It's just right there.
Yeah. Okay. And so I outlined roughly how to do it. We'll prove this maybe next time. Okay. Yeah. Sounds good.